Hello everyone. In this video, we'll be going over scalar multiplication and matrix subtraction in the context of linear algebra. So let's say we have a matrix identified as A, and it equals the matrix A sub I j, and it is an n by n matrix, meaning it's a square matrix, and C is a scalar, where the scalar is any real number. If A is a matrix and C is a scalar, we can write the product as C times A, which is equal to the scalar multiplied by each input of the matrix. So you can use minus A to represent a scalar product as -1 times A. That is A minus B is equal to A plus -1 times B. And that's how you can apply the scalar multiplication fundamentally. Let's try to use an example in this case. Okay, so say we're given two matrices with the same dimensions, and I want to deduce what would happen if we were to multiply A by 3. In the last example, I disclosed that multiplying a matrix by a scalar means you can grab the scalar and multiply it into each quantity within the matrix. To demonstrate, we have 3 times 1, 3 times -3, 3 times 2, and at this point, you already know the pattern, where it's 3 times each value within the matrix of A. Okay. By multiplying each input within matrix A, we get the matrix of 3, 6, 12 in the first row, -9, 0, -3 in the second row, and 6, 3, 6 in the third row. This is matrix A when it's multiplied by a scalar of 3. And B, what if we were to have matrix B become negative? Well, that's equivalent to -1 times our given matrix of matrix B, which is 2, 0, 0, -1, -4, 3, -1, 3, and 2. As a result, every integer within matrix B simply becomes its negative opposite. Alright. So far, so good. Now, this last one is going to require a little bit of thinking. What if we have 3A minus B? What would that matrix look like? Well, we've already got the first two parts, and the same property is the same as matrix addition, which was covered a while ago, and if you haven't seen that video, it's the same as multiplying two numbers. But in this case, you'll be subtracting. So if you were to grab part B and subtract it from part A, you end up getting a matrix of 1, -10, 7, 6, 4, 0, 12, -6, and 4. And there you go. That is how you perform scalar multiplication as well as matrix subtraction. Alright, so After the brief tutorials, we have now approached the boss battle for matrix multiplication. In this boss battle, you have a menu with the sales from the north, south, and west stand, as well as the selling price for each items consisting of peanuts, hot dogs, and soda. We are now tasked with finding the sales for 1 day in the given matrix below, and the prices of the 3 items in the second matrix are also provided. Now, how can we calculate the total sales of the 3 top selling items at the south stand? Well, let me just pull up my highlighter and let's see if we can calculate the top selling items at the south stand. Pause the video and figure it out yourself, if you know what you're doing. Otherwise, just follow along with me. So we are going to grab the south stand sales at these values right here. We're going to grab the row corresponding to the south stand, and then we're going to multiply that by the selling price given right here. Therefore, we're tasked with 207 times 2 plus 140 times 3 plus 419 times 275. And that gives us a total of 1,986.25. This grand sum indicates our sales at the south stand. Now, how can you find the sales at the north stand? And if you think it's the same process, you are correct. We would have to grab the first row corresponding to the north stand and multiply again by the same column vector, which corresponds to the selling price. So that's 120 times 2 plus 250 times 3 plus 305 times $2.75. I should have elaborated on that one, or at least fixed it. But anyhow, that sum ends up becoming $1,828.75. So the 1986, I'll initialize that as NS for north stand, and the value underneath that will be SS for south stand. Feel free to calculate the total sales recorded for the west stand. Go ahead, no, I actually do it this time. And if you calculate the west stand, you should have $940.50 as the total sales in the west stand. And yes, it is the same process. So you grab the third row and multiply it by the same column vector. Now, we have sales at each stand, and these preceding computations are examples of matrix multiplication. We could then write the product of the 3x3 matrix indicating the number of items sold, and the 3x1 matrix indicating the selling prices. What I mean by that is we can grab our prices, and this is from the matrix that was provided earlier with the sales from each stand. In this case, I have switched the north and south stands. and 190. We will then multiply by the column vector corresponding to the selling price. And after some long work, we have our product. I'm just recording these values down so we can show what our work has led to. And there you go. The product of these matrices is a 3x1 matrix given the total sales for each of the 3 stands. The definition of the 2 matrices shown is based on the ideas just developed. Now it may seem out of the box, but you are going to see as many practical applications. So, we have defeated the final boss when it comes to matrix multiplication. Now we are going to do these multiplication operations pretty common, and based on what we've done, does the commutative property apply when it comes to multiplying matrices? Keep that in mind, and if you know the answer, drop it below in the comments with an explanation. So, let's cover the fundamentals. We know that A is equal to, well, let's just say A is equal to the matrix IJ, where the matrix is an M by N matrix, and we have the matrix B, which is the matrix of B sub I J, where this matrix is an N by P matrix. Now, the theorem goes such that when you multiply A and B, you get the matrix of C I sub J, where the dimensions of the matrix will be an M by P matrix. Therefore, you get this value, or this rule right here, where you multiply the row and column of the matrix. And that is the definition of the matrix operation.